Log on, tune in, find out. Another good idea from Cambridge.
This week it's a pleasure for me today, Christopher Columbus Day, to have Irene M be the first talk. So, very good.
That's right. Perhaps they representative from Latin America, from the New World. Yeah.
And well, the title of the talk is already there. So, classical solutions for the Boltzmann transfer equation for soft potentials with data near local.
It's a kind of long title. I think I sent a different title. You've seen pieces of this lecture, some of you, and so you may get bored. I gave it last year in several occasions, and in the process of finishing all the details of the work, a few things came up that I want to discuss specifically because it really shows the it keeps on appearing the very intricate nature of the space inhomogeneous Boltzmann equation and what kind of things you can do with them. Essentially, what I will present is what you probably all of you have seen before, is the Boltzmann equation for elastic or inelastic collisions. There are two aspects I really want to discuss, so I guess this is a well-known slide for most of you, because I'm not going to use it in this form, with the exception that I just want to point out that the treatment that we do for the first part of the lecture, it can be extended from elastic to inelastic and even enter the nature of what is called viscoelastic interactions that corresponds to inelasticity or local inelasticity that depends on the impact direction of the collision. And there will be two aspects of it. One is to understand how to get estimates of the Boltzmann equation from a different point of view of what they have been done so far. Essentially is go to the weak formulation and see that you can recover very nicely Young's inequality and Hardy-Littlewood-Sobolev inequality for soft potentials. And then we are going to use that estimates to obtain classical solutions of propagation of regularity in LP spaces for the Boltzmann equation with soft potentials. Okay? And we also revise that is something that has not changed at all, the construction of solutions for soft potentials within a range, so it cannot be too soft, in a range for which the Kanier-Schimbrett iteration applies, because, and we are going to do this near Maxwellians. I will remind you work that was already done there. What we do in this form is it was a new way to get estimates, an extension to a larger class of initial data, but essentially gives you not only the construction of existence, the existence is in L infinite, so you have bounds, with respect to the subnorms, and also you have uniformity in time. Okay? And I would explain you very well under what kind of conditions the whole program applies. Okay? So now I have it, so maybe a pointer would be of use.
Because only the big
And you have the stick.
Okay, that's all right. Oh, okay.
Speak soft and carry the big stick.
Yeah, impressive. Let's dig in there. So the characteristics of the things of the properties I'm going to be looking at. Let me remind you what is now I'm going to be considering from now on the Boltzmann equation written in the scattering direction sigma. This is what is also called center of mass and relative velocity coordinates. And the collision kernel takes the classical form. You have denotes the renormalized relative velocity. and sigma is the direction of the scattering function, the scattering angle, which is always defined, as Sasha told me, as the post-collisional, the direction of the post-collisional relative velocity in the specular reflection, even if you do elasticity, okay? And so if you do elastic theory, sigma is really the renormalized post-collisional velocity. So what I'm going to be assuming in the function b, the differential or the angular function b, I'm going to assume that it's a sort of, maybe this is something I invented, weak Gratz assumption. The grad cutoff assumption, I like to think of it as being L1, and that will be enough for the construction of the existence. But for the regularity, I need a little bit more, L alpha. And I want to show you why, okay? It's actually an interesting intermingle of LP theory and the nonlinear, somehow, nature of the equation. Okay, so the classical grad cutoff assumption is when alpha is equals to 1. In some literature, you will see that the grad cutoff means that B is bounded. So what I mean by grad cutoff is integrability. So whatever, independently of what you interpret that, the interesting thing is that the grad cutoff, in the way I use it, allow us to separate the gain from the loss. And that is where the Canier-Schimbrot iteration that we use is successful. I use that separation, okay? So for instance, there's a whole range of potentials, which would be short-range interactions on which that function would have integrability up to, for instance, in 3 dimensions, up to n, up to lambda equals -2. Okay, so which enters into the range. So then the equation now is written in the form as I had it before, and we call R of G. The collision frequency, if you look at it, comes from I would say, the non-local part of the loss operator. And so there is a couple of remarks I want to make, because the next part of the lecture will focus, the first part of the lecture will focus on this statement. The first remark is that the existence theory for source potential, we do it by Canier-Schimbrot methods, only requires alpha equals to 1, okay? And so you can do it with integrability of B, and it also goes from -n+1 and lambda. In fact, sorry, I should have put it's less or equals than 0 if we do the existence theory near Maxwellian data. If you do the existence theory of the Canier-Schimbrot iterations near vacuum, you can go all the way up to hard spheres, okay? But for soft potentials, you do it near 0 because you need some, for near Maxwellians, you need some uniformity with respect to time that you cannot do for lambda larger than 0. The other observation is perhaps the most significant of what I'm going to say next. And it's that if you look at the loss operator, that is a bilinear form, and you can see it here, that it has, well, not perhaps here, we will see it later, but if you, oh yes, it's, as I said here, it's F times R of G, and R of G is an operator that has convolutional structure. I'll write it for you again in a short while. However, so it's a weighted convolution form, and the weight comes from coming from the potential in relative velocity. But however, the gain is actually a weighted symmetric convolution structure. It's non-local either way you look at it. But the loss is local with respect to one variable. Okay? And what does it bring to us is what I will explain in a minute. And then I will show you the second part of the lecture is after I do the existence theory and I want to study the propagation of LP regularity, then what it comes up, because I use the estimates that I'm going to derive from the convolution structure of the Q plus operator, I would need a little bit more of integrability in the collision cross-section in order to get the propagation of LP bounds and stability in LP. Okay? I should say that there is a work of Ha and Yoon, which they proved in 2006 the stability for the Boltzmann equation for soft potentials in L1. And that particular work uses that the function B is bounded and need to do some surgery or cutting off near 0. We actually extend that result to conditions on integrability. And it's a little bit more, it's this alpha integrability, and it also, we extend it also to LP for a P in within a range, and you see where the range comes from. And so when we started to work with this, first with Emmanuel and Ricardo Alonso. Emmanuel Carneiro and Ricardo Alonso were a couple of graduate students. Ricardo was working with me, and Emmanuel was trained in harmonic analysis in Texas. Did a lot of interesting stuff for sharp estimates and so on. They came out with a very nice observation, wrote the first paper, which was essentially how to get very good estimates of the Young's inequality when you have sharp constants. And exact constants, and how can you prove that they are sharp? We wanted to extend that to inelastic collisions, and that didn't work because they used the Kahneman integral representation, and there was a lot of difficulties in making it work properly. But then we realized that, in fact, there is a very nice structure on the equation that we can exploit when you write on it in a weak form. That you have seen, some of you have seen, but essentially let me just now start it. If I look at the Q plus operator and I multiply by a test function, what I obtain is that this is going to be written in this form, and after you change coordinates in relative velocity, that's a typical trick, it's a convolution multiplied by a weight. Okay, and this is something that I will show you in a minute what is that weight, and that uses in principle the integrability of this of the B function. I should say that even if I assume that alpha the integrability is in L alpha, you will see how it comes later on, but it certainly is going to be also in L1 if alpha is larger than 1. So that would not be a problem. So in all saying is just, and in what I wanted to say now, if you write the Q plus operator in the center of mass and relative velocity direction, which now I denoted here by omega. Before I call it sigma, but that's you should not care about that. I should care about that, not to get confused. But essentially, you can trace down. So here it should be omega, not sigma, or the other way, actually. But then you classify so for those that may not know what is soft potentials, it refers when this exponent is negative. Where is the exponent? Okay, when B, the exponent is negative, Maxwell molecules for 0 and Haar potentials for above 0. Haar spheres is 1, Haar lambda 2 is super, how is it called? Super Haar spheres. So the convolutional structure I was talking about was the following, and this is something that we fully developed. You know, there is a work, for instance, of Devillet, the work of Sasha. Many people have written the equation in one way or another, and it was all moving around. Okay, what we do is a very different closed expression that allow us to manipulate better the estimates. Okay, so it's so essentially it's the following one. I just take the Q plus operator, test with a function, and I can see that this can be written as a convolutional structure, as a bilinear form, multiplied by P function acting on U. Here is the potential part of the collision kernel, and the angular part is embedded here because this P takes this particular form. Actually, if you go to the first original paper of Carneiro and Alonso, I have to say that when they came, they didn't use this weak form. They did in a strong form, but they defined this operator in the stage of their estimates. And they call it the Bobilev operator. Hi, Irina. And why you call it that way? And they call it that way because of this property. They relate it to this property. Sasha didn't like it, I know. Yeah, and so we changed it because you didn't like it. I think I call it the angular mixing operator. Okay? And but if you go to their paper, that's the way you read it. So, yeah, this is angular mixing. So basically what allows you to do is, you see, you pick up the test function, right, and evaluate it in these particular variables, right, and that, which could be elastic or inelastic, and do it now in the frame of the scattering direction. Center of mass relative velocity gives you the correct way to get a full representation that you can manipulate on the estimates. Okay? And as I said, in the work, this operator, you may associate it exactly as you take the Fourier transform. What you get is exactly that operator acting on the two Fourier transforms of the function, and this is in the theory of Maxwell molecules that Bobilev developed in '75. But essentially, the observation I wanted to say here, before I move the slide, is that you can see that the Q plus is a bilinear form which has a convolution structure, and we call it a symmetric weighted convolution structure, because no matter from which side you see it, it's a convolution. You would have to change the form of the P operator. So you wonder, is that the same for the loss term? And the answer is going to be no. I may have missed one slide, or maybe it's later. And so what can we do with a Q plus? Okay, that would come later. Okay. So what we can do with a Q plus, with this symmetric weighted convolution structure, is the following. First, that if you look at the hard spheres, variable hard potentials, you could go, as I said, up to higher orders of lambda for as long as the theory allows, but include Maxwell molecules. You get the Young's inequality. So this was in fact developed by Gustafsson in '88. It is developed further in the thesis of Clement, and which is published in a work with Cedric in 2004. So what is new here at this level is that this representation allows us to do a truly exact calculation of the constant, okay? And characterize it fully as a function of the exponents P and Q and R and the alpha. And I will show you how it comes that. And we can actually prove that that constant is sharp in the case of Maxwell molecules. That observation was done by Alonso and Carneiro in the first paper. And it's very beautiful. They find what is the sequence of functions that realize the norm, or realize the inequality. Okay? We extend it here to the inelastic collisions. For for the soft potentials. What the soft potentials have is that this is going to be, instead of a Young's inequality, is what you would expect to have when you have convolution inequalities with singular forms. Because now the potential part, so you have a sort of weighted convolution, the weight has this distributional angular mixing operator, and the singularity actually calls for the Hardy-Lidwell type of approach. This was observed in a work, for instance, of Alexandre and Villani back in 2000. So basically what they did is they estimate the collision operator and they end up using the Hardy-Lidwell Sobolev inequality. So what we obtain here is somehow a slightly better inequality on which you have that the Q plus, it will satisfy a true Hardy-Lidwell type of inequality. And I will show you is that the ways we prove it is by means of what you would call a Brashkan-Lieb type approach. So this is, in fact, we apply pretty much the ideas of Brashkan-Lieb and Luttinger. It's not the same as Brashkan-Lieb and Luttinger, it's a type of. And you see how it comes up. So as I said in both theorems, this constant depends on all the parameters into the game. They are explicit and depends on the bounds that you get for the angular mixing operator. And in fact, the constant is going to be an evaluation on a maximal function acting on the angular mixing operator. Okay? And you can really, because this P operator is invariant under rotation, so you do an averaging of that invariance, then you pick up that the maximized, the LP norm is going to be preserved, but that operator, and is picked up on actual functions which are perfectly isotropic. And then you do the constant, it's a calculation of a one-dimensional integral. Okay? So the theorem, in a sense, in a way, this theorem is giving the convolution character of Q plus as you have, but it's the convolution character as a symmetric form. So let me show you the sketch of the proof. This is pretty much, you have seen, as I mentioned before, we need to do a radial symmetrization first of this angular mixing operator, and then we show that it maximizes the LP norm. Also, the average over rotations actually preserves the LP norm, and so that means that when you do the maximization for the Hardy-Lidwell Sobolev estimates, the constants that you are going to be picking up are going to be determined by simply the evaluation of a symmetrization, of a radial symmetrization of the test functions that you have used, evaluated as a function of just a parametrization of the angle. So if you have seen Maxwell molecules, really, the calculation that you need to do for instance, analyzing isotropic solutions, this is exactly what appears in the Fourier transform of your radially symmetric operator for Maxwell molecules. Okay? And that gives you the constant. Okay? That gives you an exact calculation on these radially symmetric functions in the LP norms. I think I missed the tilde there, but anyway. Okay, so I should say that all of this calculation you can do it for elastic or inelastic, and again, it's like the work we did with Sacha and Jose. If you go back, in fact, these functions appear here is exactly what we use in the inelastic case calculation 10 years ago. So then you can obtain immediately, after you sort of define this P tilde operator, which is this calculation on the symmetrized, angularly symmetrized functions or average functions, then you have what I like to call an angular averaging lemma. So I don't mean to have big words. I wouldn't know how to call it any otherwise. But this is what this operator is doing. It's really giving an estimate on that mixes all what is in the angular part. And then in that case, we get that you take so you obtain essentially a Young's inequality for the operator. And you know exactly what the constant is. It's exactly given here. Now purely in terms of the dissipation parameters if there, or if not, you just can calculate it. So this is the new part. I should say that if you go to, there is a paper of Rasyanov and two other authors. It should be, I think I have it in the things, where they did the calculation of this constant because they actually do it for the elastic case. They don't do it for average rotations for the case of L1. Okay? I mean, or LP-L1. I mean, I have to, it's quoted in the manuscript. So we will extend it to all directions, and we do it, so we do it for the whole range of exponents, of convex exponents in Young's inequality. And you'll see why you need it later on for the regularity. So in particular, then, once you have this estimate of the manipulation of LP norms of the P operators in order to obtain this constant for the test function, then you can nest it that. It's like really a nested estimate that you need to do, because here what you want to do is the integration. Okay, so you want to calculate, remember we want to get the calculation of the LP norm of Q plus. So you do it as a classical dual approach to LP norms. You test by a function that is going to be in a dual space, that is going to be the LR prime, and then try to see what you obtain out of it. Well, if you write this form, so you know that you have the convolutional structure, okay? And then when you start to see what you can do, I mean, at this point, I mean, this is what we call, in fact, I should have, I want to say at this point, because it took us a while to understand the many of the pieces together. When we wrote that, we did not realize, we have a first draft, and we realized that there is something that we didn't observe. I have to say that I was walking one day with Luis, and I'm telling verbally what we do. And he tells me, oh, that looks like a Brash-Leib inequality. I have no idea what it was. Didn't pay attention. It was completely gone. And then we were with Eric Carlin and Ricardo Alonso, and we explained the work, and then Eric said, oh, that looks like a Brash-Leib inequality. And then at that point I said, we really need to dig in what is this. And indeed, I have never studied deeply this kind of inequalities. So you go in, and it's almost like a Brash-Leib. It's not quite, because a Brash-Leib inequality here, it would not be, you know, they only allow for functions which have acting on linear transformations. You could do rotations, you could do translations. But you cannot, but this is a very nonlinear operator. But it has this invariance under rotations. And it has this ability of, you know, preserve the invariance, preserve the LP norm. So it's a very special nonlinear operator, which is this mixing. And so in particular, this structure, you do something like that. When you look at the way Brash and Leib do these multilinear estimates of multilinear convolution-like inequality, they really start to distribute exponents in an optimal way, and they write convexity exponents. And this is exactly what is in here. Okay, so the final version of the manuscript actually has all of this well explained. And so these estimates resemble a Wegner-Brash-Leib type of argument for a nonlinear weight with best exact constants to get the Young's inequality. They did it actually for a Fokker-Planck type of operator. So this Sobolev inequality, where everybody used the best constant of Wegner and Leib and so on, is the analog. Somehow the analog for the Q plus. And And so, and you can prove that the constant is sharp for Maxwell molecules. You don't know how to do it for any other potential, and may not be actually true. So let me now give credit, as I mentioned, it's the work of Gustafsson, Villani, and Moreau. They use in that case the B constant, so it can be extended to integrability in B as a bilinear form, and I will come back to this point. Because as non-bilinear form, when you use it on FF, you have to prove that this constant is positive, and that requires more integrability in B. And you see it in a while. And so the other thing I would like to mention, that the dependence on the weight alpha. The weight alpha, what is the weight alpha? Let me see. You can do, let's see, for those that, let's see, Vlad is in the audience, and Sasha. You can actually, we did a lot of estimates of L1 weighted. This is a very fundamental estimate, for instance, to obtain not only the properties of moments, but the property of summability of moments, to get that the solution is in L1 exponentially weighted. And this is something that, for instance, Clement uses a lot in his very recent results for decay to equilibrium, or to get the tertiary conjecture in the space homogeneous setting. So one of the things I have not explored is one could actually do better by putting weights into these LP norms. Neither it would be necessary for anything, but it may be there. We have not done it. I mean, the argument of trying to write infinite inequalities for the moments and try to see that you get a summability condition for that particular expression. It may work, it may not work, I don't know, but that is an interesting point that maybe it could be obtained. The corollary is that for Maxwell interactions, you can get sharp constants, and that is that you obtain them directly by finding a sequence that realizes the norm. Okay, so that is actually that part you saw last year. So next is what happens for the Hardy-Littlewood-Sobolev. I should say that for the hard potentials, the manipulation of the Q minus is exactly the same, okay, as I had it before. So the problem that I just mentioned of integrability comes now for the soft potentials, on the more integrability on the differential cross-section B. So how does the Hardy-Littlewood-Sobolev inequality work for soft potential? Again, if you look at Branch-Littlewood, how he did Hardy-Littlewood-Sobolev and best constant for Hardy-Littlewood-Sobolev, it's exactly the same thing. It's just write it, as a bilinear, as a sort of multilinear, if you wish, expression, where there could be convolutions. The difference now is this nonlinearity form that has this very special structure. And here you would have something that now is singular. I write it lambda, but I take it negative, okay? So this is a singular exponent. And that is what he calls for Hardy-Littlewood-Sobolev type of argument. And indeed, what you do is you distribute properly. So again, this is an application of Hardy-Littlewood-Sobolev, with the exception that you really need to work a little bit careful into finding an intermediate value of A, okay? Because here you're going to put the psi in LR prime, but then you have to find what is the exponent that corresponds to this one as you do this disintegration of in other words, of this estimate here, which you need to estimate here, and you need to find what is the exponent A that you need in this particular form, which is is the squeezing out of this estimate. I mean, it's using the Young's inequality on this P estimate. Well, if you look at it, then you have to see that you have to find an A such that it's possible, and it's conjugate A prime, such that it's possible to have this inequality, constrained to the fact that also you will have some tie-ups between the R, the P, and the Q, right? And in that case, if you succeed, you know how to write the constant. And then when you do that, this is exactly what I said, is it possible to make such choice of A in such a way that I can obtain this? And then you write all the conditions and constraints that you need. And here they are, because you have to have all these constraints that come up from the different exponents and the different exponents, the fact that you have the singularity on U that needs also in the Brush-can-live argument the absorbed by the integrability, and that is what it forces a condition in the Young's inequality that depends also on the singularity of the exponent and the dimension. And all of that comes together in a set of actually 5 unknowns and 5 equations with, 1, 2, 3, 4, 5 equations with 5 unknowns, which are this P, Q. So is it possible? I mean, it could be an empty set, right? And then it turns out that the answer is yes. It's possible to find indeed an A such that it would satisfy this inequality. So these 5 identities comprises into that one of A would satisfy this double-sided inequality. But that happens only provided that R is less than Q. So at that point, you say, well, but what happens for the other range? Hard spheres was for all possible range. So how could we do further ranges? Well, you realize immediately that in that particular case, it tells you what the constant is, and you can trace it down. The C2 and C3 are going to be the corresponding Hardy-Littlewood-Sobolev inequalities, which were computed sharply by Lieb. So what do you do to get further exponents? Well, to get further exponent, what you do is you use the Q plus representation in the symmetrized weighted form, in the symmetrized convolution, or in the alternative convolution weighted form. And then you switch the role of P and Q, or in your estimates, or the role, or R and P. And then you can obtain in that case also the estimate, but now R is less than P. In the previous one was R less than Q. Now R is less than P. And then to complete the argument, you use the Ries-Thorin interpolation theorem to do the maximum by just classical interpolation. You get it for the Q plus, and you recover exactly the range of parameters for Hardy-Littlewood-Sobolev and Hardy-Littlewood-Sobolev inequality, HLS inequality. So what happened with the Q minus? Well, the Q minus, we thought at the beginning it was going to be in all range. In fact, we had missed the fact that we needed to split and look at the change, sort of looking at the convolution structure of the other form. And then when you go to the Q minus, you realize that the Q minus is not a symmetric convolution structure. The Q minus is always local in F, or local in whatever. You fix one, it's the first one, and it's local in one, and it's a convolution in the other. And that immediately constrains the range of R's. And then he says, well, how do I finish the argument? I cannot switch because I don't have the non-locality in the two variables. And in fact, we realized not only that, it would be false. We actually found a contraexample that is very easy to construct that would violate the estimate for the Q minus. So you can actually find particular function phi for which you take this particular form of the potential, and then you see that the Q minus will blow up we have a pointwise blow up. So it was actually very interesting, and that actually forced us to constrain the range on which of the LP exponent that you can use, for instance, for the regularity as you try to study the propagation of LP norms for the Boltzmann equation. So it's just an observation. I don't know, maybe somebody have been able to pick it up. I don't think this has shown up before in this form, but I'm not sure. Maybe Clement, maybe you know that better. Okay, so then an extension of the results is something very nice, very nice. I mean, actually, the extension is not that it's very nice. The extension is okay. We obtain how to get norms in any LP by weighting the Q plus with Maxwellian. This is something that is very important for many estimates that may care about decay rates. And in fact, this was recently used by Alonso and Lodge in a very nice calculation and revisiting the work of Clement Moureau and Stefan Mischler and Ricard for inelastic collisions. And they can go and obtain, in a very rigorous study, in a very straightforward form, recover the decay rates of half law for any variable Hart potential. And that is something that some of you would know. Yes?
Just a question.
Yes.
M lambda, it's M gamma? Or?
No, in fact, we can actually put any, you can put the weight. Oh, okay, yes, okay, yes. I mean, the weight you can actually put it on. It may be the Hart sphere or not. You can change the weight that you want.
Yeah, lambda is related
to the.
The weight is it a Gaussian weight or is it a stretch weight?
No, it could be any stretched, precisely, because for the study of inelastic collisions, you need it for any stretched. And but in any case, for the elastic case, it's an estimate, and this is what you get. This is an independent of the application. Okay, so you can put any stretched and calculate it, and in fact, it turns out that the inelastic case is better. We can talk later. For instance, the work we did with Vlad and Cedric or even Sasha originally will cover. If you put L1, for instance, you can do this exponentially weighted tails, and it's the study of summability of tails.
The same that we were in B, the cross section.
Yeah, it's in here.
And in
Yeah.
Maxwellian.
Right, that's right. Yeah. But I guess I would have to. I don't remember now if we can extend it. No, it's in the cross section. It's Hart spheres. Yeah, from Hart spheres to super Hart spheres. Yes. Yeah. Right. It would be another way to obtain very quick the kind of estimates we use. Yeah. This is an estimate that comes from the Q plus. Then the question is how you use them. For instance, you use an estimate of this kind to do the creation of moments. It's L1 with a weight, and you put the lambda that depends on. Okay, it's too technical. You have to go to the lower moment. In the work we did with Vlad and Cedric, we could do the lambdas here, right? But we have variable Hart potentials. We did it between 0 and 1, but we can show the calculation, the bound, with a Gaussian. And we show the propagation of that. Okay? The question is how you use it, but you can visit it and do it for a large range of weights. Okay? Then the question is how you use it. That's the most important aspect. But in any case, you can calculate it. So let me show you now how you use it in this particular setting, which is the soft potentials and the propagation of LP estimates and stability. So in the soft potential case, I'm going to go very fast now. The first is that we are going to solve the solutions in spaces with initial data that are going to be trapped. You can do the near vacuum theory, and that is well established, and I'll skip that. But the interesting is the initial data for soft potentials when you have, say, two Gaussians that have to be close in a notion of a distance that I will give you in a while, and you can put anything in between. So it's sort of that the initial state is, say, local to it, near to local Maxwellian. Okay? And then what we do is the Canier-Schimbrot iteration allows us to do the construction and find L-infinite solutions within that band, provided that the band is fairly small. Okay? Let me show you what it means by that. The first slide has a few notations that you all know, the definition of Malp solutions along the derivative or distributional solutions or the spaces M, alpha, beta. Now, I'm sorry, you are going to find two alphas, okay? And I will tell you as it comes up. But it's for this M, the first exponent denotes the decay in X and the second one in V. And then what you see is that I sort of recall here the Canier-Schimbrot iteration is a double-nested, it's like a Pynchon theorem for the Boltzmann equation. It's a double-nested distribution. The way Canier and Schimbrot realize is that if you put initial data that is near vacuum, the Q square becomes lower order and it's gone. But if you want to deal with a near Gaussian and the data is large, you have to do something with it. Okay, and that is what we did. In fact, this is not our first idea. It was a study of solutions by Canier-Schimbrot near Gaussians. The first paper is from Toscani in the early 80s, or even 78. Giuseppe looked at that many years ago. And he does it in a setting, and so it's 88. Then there is a paper of Boudon, which he does it by sort of a Schauder type of estimate, and a paper of Estefan, Mischler, and Benoit Pertin in 97, where they do it for infinite mass for soft potentials. And again, the class of initial state is different. So what we do here is somehow it's a revision of that. We enlarge the class of initial state. What is very interesting here, in view of somehow decay rates, is that this particular solution is going to be like a heat flow. It's going to spread its mass because it's trapped. You see, this is the construction of a near-infinite solution of a mile of the mile form of the equation. You start with a Gaussian state. It's going to be trapped here, but then this starts to travel in times, right? Which is the upper and lower bound, and that means that it has decay in time with the rates that come from these two rates, which are not necessarily the original ones. And it gives you decay rate in time. Okay, it's fully trapped. So that is that was reported in JSP 09, and I should say that the work on of the convolution estimates and resemble to HSL inequalities is in Communications Math Physics of this year, and so let me show you briefly before I finish, because I have how much longer? 5 minutes? 2 minutes? Okay, 3 minutes. So then let me, you trust me that the constraint of the range of the soft potentials, you cannot go to all the way -1, comes from this estimate that gives you uniformly in time. It will come up later. That was very well known for all the people that have been using Canier-Schimbrot. The form of what is the distance of the two Gaussians, the constraint of that you will have on the initial state, means the following, or we define distance in between Gaussians is the distance in the rates in X and V, but also in the amplitude. And under those conditions, what we can write is a sequence of minimizers and maximizers for the Canier-Schimbrot iteration. So you have to have an upper sequence that converges down and a lower out that goes up, that is going to pinch. That it can be done in within that it satisfies what is called beginnings condition, that you would have monotonicity in the construction, and you can do it, okay, and you can do it provided that the initial data satisfies these constraints, okay, and here is how the rates of the Gaussians show up in here as much as the bounds of lambda. And so the last part of the lecture what I want to say is how do we get classical solutions? So you start with an initial state in LP. Does it propagate? That's an open question. I mean, it's an L-infinite solution. It was not studied as far as I know. And so the first observation is that for the Q+, now we're in soft potentials, you need to use Hardy-Lidwell Sobolev inequality. So for the Q+, you can visit all the ranges. For the Q-, you cannot. But you also need that the Q+ has that estimate, that constant C, finite. This is something that we actually, I have to say, I'm ashamed that in the paper we published in last year in JSP, we didn't check that. I wrote it, and it says that is the constant. Is it finite? What does it take that constant to be finite? And then we just realized that if you want the constant to be finite, you need to add a little bit more of integrability to secure it. Okay? And in fact, this more integrability, and that comes from the natural form that you would have as you write the Q+ operator in FF. This is something that, for instance, when you do estimates with pointwise bound, that's why you need to cut what happens at 0 with it, with a collision, with a differential cross section. But here you can actually compensate by asking a little bit more of integrability. And so essentially what we get, and let me just say it in the next slide. So in order to estimate the gradients, we need a little bit more of integrability in the angular cross section. And the integrability comes from here. So basically what we do is we grab the integral you had from before and says what does it take actually to make that integrable by doing sort of control of Cardan analysis, and the integrability is alpha prime denotes a convex number, and we get a condition. It depends how it relates to the dimension, because the Q- has a constraint on the range of the LPs, right? Then it turns out that we can actually obtain this estimate, and so it's a control of the gradient in X by the gradient of the initial state in LP, where P has to be between 1 and beta of alpha, and that beta of alpha is going to be exactly the minimum between the initial state, this quantity, this could be, depending how this is, the quantity is at 1, it could be any range, if not, it is constrained, and this number, because that constraints come from the Q-, okay, from the Hardy-Lidwell Sobolev from the Q-. And then you said, is this possible? Could that be, I mean, is it possible to pick up a beta of alpha that is larger than 1? The answer is yes. It's a stingy. It's a very small range. Okay? We could enlarge it, perhaps doing a better estimate. We have not used in this calculation the fact that I have a lot of decay from the solution in L-infinite. We just use this handling of exponents. So it's room for improvement. I mean, room for improvement would be to enlarge this beta of alpha all the way to here. You cannot pass that because there is a counterexample. Unless you start to squeeze very careful on different potentials. Okay? But it's somehow like, I like this in a sense, it resembles the kind of LP regularity theory of nonlinear PDEs, right? People, I cut it in a minute. It's people that does nonlinear Schrödinger or the wave equation, they very carefully have to look at symmetries and how they pick up the initial state and how they pick up the space in such a way that they get all this balance for the equation. And then to obtain the proof I pass it, the same thing you can obtain for the gradient in velocities. And just let me say the last slide by using sort of Gromwald-Bernoulli type creation of moments estimate. All shows up there naturally. The last one is the stability estimate that indeed comes in within this range under the conditions we had before. And that's all I wanted to say. Thank you very much for your attention.
Any more questions?
Questions coming. It goes back to a discussion I had 2 days ago with Clément. Can you go back 2 slides away
2.
One.
Oh, I went actually fast at the end.
One.
Maybe.
One more. One more. There was one more, maybe. There was a constant C, capital C somewhere. Line is you have LP. It's very important thing.
Yeah.
Yeah, this C layer.
Oh,
it depends. Okay. The question
This is what we computed sharply in the first part of the lecture.
assuming that in some case
Yeah.
you could reach a macroscopic state, hydrodynamical. Then it's known, I will go back to Lippmann, that the Prof and then Jeff Roach, that you don't have uniform estimate in any other LP than P equal 2. When you have the problem are badly posed, the way non-linear wave equation, linear Euler are badly posed in dimension space greater than 1 in any LP that is not P equal 2. That's the same thing as the street chart estimate.
Okay.
Which means that your C here, if you have the parameters of the scaling that goes to the incompressible limit or to the macroscopic limit, should blow up in some sense. I see it, by the way.
That's very interesting because you see
infinity already, but I wanted to make.
Yeah, well, okay, the gradients may blow up. That is true. I mean, the initial data doesn't need conditioning the size. It's actually interesting.
No, but then the C.
Sorry?
But then you have the condition in the C.
You have the condition in the C. It certainly depends on P. P is constrained, but this P, you see P, because you have the constraint on the loss term, so P is going to be less than this beta alpha, and beta alpha is the minimum between this P0, the beta 0 that I showed you before, and the n over n minus lambda, or n minus lambda over n, sorry. Okay, but what I'm saying is, of course, there is a constraint. And in fact, let me show you, because in fact we do have this is very interesting comment, at least for me, because, where is the constraint, sorry. So the constraint, I have it here, but I want to say where I have the beta 0 is here, and yeah. So basically, what we proved is that for this has to be a strictly less, okay? And at here, I know I have a blow up coming from the Q plus.
Okay.
So perhaps it's a very interesting comment. It may be, or at least I can find a contraexample. I'm not saying that it will blow up all the time,
No,
but maybe I should look. But what I'm saying is, it's clear you cannot, I wish I could enlarge this range. This is what we thought at the beginning it would happen. That's not true. It is a constrained range. And that actually may be related to an observation of that kind. And it's already the lack of non-locality of the Q minus. I always thought that the Q minus it is a better term than the Q plus, and the more I learn about this equation, the better the Q plus is getting, and the worse the Q minus is showing up.
Any other comments? If not, let's thank you again.
Okay. Oh, okay. We have a second.